In this lecture, we're going to talk about national parks that have igneous rocks. There are three main types of rocks. There are sedimentary, igneous, and metamorphic. And many parks have one or at least one, obviously, but more than one type of national park, but type of rock. But here we're going to focus on parks that the predominant rock type is igneous. So here we got Yosemite and Hawaii Volcanoes National Park. At first, you wouldn't think they have much in common, but one thing that they do have in common is that the predominant geology is igneous rocks. So again, we can see Yosemite Valley here, and then we can see Kilauea Iki here, which is kind of a valley created by a lava flow that started in the 1950s. So here's our friend the rock cycle. So again, there are three major rock types. There are igneous, sedimentary, and metamorphic. It's a true rock cycle, or a true cycle, rather. There is no beginning, there is no end, but we can kind of think of magma as being the beginning. Magma is simply melted rock. And when it cools and solidifies, crystallizes, it forms rocks we call igneous rocks. Over time, those igneous rocks, if they're exposed to land surface, factors like rain and temperature and fires can break those rocks into smaller bits, what we call sediments, like sand on a beach or clay at the bottom of a river, or gravel at the bottom of a river. And over time, those sediments can be basically lithified or glued back together in rock we call sedimentary rock. If we bury those deep enough and add heat and pressure, we can get them to recrystallize without melting. We form metamorphic rocks. And if we continue to heat them and eventually they melt, they turn back into magma. Now, there are different ways that we can short circuit this. We can weather metamorphic rocks. We can weather other sedimentary rocks. We can take metamorphic rocks and add heat and pressure and turn them into other metamorphic rocks. We can take igneous rocks, add heat and pressure, and again, turn them into metamorphic rocks. So there's different ways, again, we can short circuit the cycle. So again, igneous rocks form from the cooling and solidification, what we call crystallization of magma. Sedimentary rocks form from bits and pieces of pre-existing rock we call sediments. Again, things like sand, clay, silt, gravel, pebbles. Metamorphic rocks form from the recrystallization without melting. So magma is molten rock. It is liquid. It also will sometimes have solid or gaseous components to it. Magma that flows out onto the land surface is called lava at that point. So as magma cools, the ions, the atoms in the magma, the little cations and anions, will start to arrange themselves into crystals. And so the longer it takes for it to cool, the longer there will be time to grow crystals. And so as a result of that, the larger the crystal size generally indicates the slower the cooling rate. So if you have rocks with very large crystals, maybe a half an inch to an inch in diameter, that indicates a very long, slow cooling, usually deep underground, where the heat takes a long time to escape from the magma. Rocks that have very, very tiny crystals, microscopic crystals, are barely visible to the human eye, or crystals that, well, maybe no crystals at all. Maybe it's what we call glassy. And that indicates a very fast cooling over a period of maybe days, weeks, maybe a few years. The slow cooling rate usually happens over thousands of years. So here we can see different places that magma and lava can occur. So deep underground in what we call batholiths and plutons. Those are what's going to give you large crystals. You get some medium crystals from these other igneous intrusions we call sills and dikes. And then finally, if it flows out as lava, then you get very fine crystal size, usually what we call aphanitic, which are microscopic. So if rocks cool deep underground in large magma bodies, we call them plutonic or intrusive. If they flow out onto land surface and cool as lava, then we call them volcanic or extrusive volcanic because they flowed out through a volcano. There are two main types of lava, and these are Hawaiian words. The first type is what we call pahoehoe. It's a ropey lava. I'll show you some photos in a minute. And the other type is aa, which is a broken, chunky lava. And these are basically the result of what we call the viscosity of the lava, and that's its resistance to flow. So as the lava is very, very hot coming out of a volcano, it's going to flow fairly easily and you get ropey lava. As it starts to move away and flow away from the volcano, it's going to cool down, it's going to thicken as a result of that, and instead of flowing easily, it'll break into chunks and pieces, and that's how we get that chunky lava. And different types of textures, if it's very fine grained, again, microscopic or barely visible to the human eye, we're going to call it aphanitic. If it's coarse grain, large, easily visible crystals, maybe 1/4 of an inch to 1/2 an inch in diameter, we're going to call it phaneritic. Porphyritic has two crystal sizes, large, easily visible, set against a background, what we call a ground mass of aphanitic crystals, very tiny or microscopic. The larger crystals are called phenocryst. And then glassy is where we have no crystals. We can look at it under a microscope. We're not going to see any crystals at all. It cooled too rapidly for the anions and cations to arrange themselves into crystals. If we get a lava and magma generally have dissolved gases in them, gases like water vapor, carbon dioxide, hydrogen chloride, which is basically hydrochloric acid. And when this lava erupts out onto the land surface, those gases, which had been under pressure, are now released and they form bubbles. And if there's a lot of bubbles, it gives the lava a frothy texture, like the foam on top of a soda or whipped cream. And we call that a frothy texture. If there's a few bubbles, not, frothy, not like whipped cream, but a few bubbles like in a soda or carbonated water, we call that vesicular texture. So here's our textures. Here's a granola bar. That would be phaneritic, easily visible. We can see the nuts and oats and raisins and chocolate chips. Here's a sugar cookie, an example of aphanitic. So we've got little tiny sugar crystals in there, but they're too tiny to see with the human eye. They would be aphanitic. And here's porphyritic. This would be a chocolate chip cookie. We've got these large, easily visible chocolate chips, but they are scattered among this fine, kind of like a sugar cookie, this fine cookie with really tiny sugar crystals. And again, just showing you different places where they might occur. So phaneritic would occur deep down here, but the rest of them, aphanitic, frothy, and porphyritic would occur on land surface. So here's aphanitic. You can see little tiny specks right here, some dark crystals, which might be either hornblende or biotite. But otherwise, it's kind of this homogeneous looking, kind of pinkish, tannish rock. You can't really see the crystals. You'd need to look at them under a microscope to see them. And that's aphanitic. And compare this, where you can see these pink crystals are potassium feldspar. The darker crystals, again, probably hornblende, maybe some biotite thrown in there. And the clearish, grayish crystals are quartz. Okay, same crystals as that previous picture, but in this case, we can easily see the crystals. In the previous picture, the crystals were microscopic. And then this is porphyritic. We got these large, what we call, again, phenocrysts, these lighter kind of cream-colored plagioclase crystals. And then this medium gray, what we call a ground mass of tiny or microscopic crystals. And this results from the magma starting to cool deep underground and forming these large crystals. But before it finishes cooling, it's kind of a slush. It erupts out onto land surface. And as it erupts out on land surface, it cools fairly quickly. And that's how you get this fine-grained ground mass. And here's our glassy texture. This is volcanic glass, also known as obsidian. There are no crystals in here. This is just glass. And here's our frothy texture. The resulting rock is called pumice, and most pumice is so light, so low in density, it will actually float on water. There are two types of compositions. The composition of an igneous rock is simply the chemicals and minerals that constitute that rock. So there are two main groups, and then some other groups as well. So ends of a spectrum are mafic rocks. These are going to be dark rocks with dark minerals in them. These rocks are rich in iron, magnesium, and calcium. They are low in silica. There are felsic rocks, and these are lighter colored rocks. And these are going to be rich in potassium, sodium, and aluminum, and have a higher silica content. Okay. So in general, mafic rocks, because they're low in silica, generally will not have any quartz in them. Felsic rocks, because they're low in iron and magnesium, are not going to have things like pyroxene and olivine in them. So felsic rocks, again, have a high silica content, about 70%. Of the rock is made out of silicon dioxide. If it's coarse grain, we're going to call it granite. If it's fine grain, we're going to call it rhyolite. And granite constitutes the continental crust. So just getting back to those food examples, here's dark chocolate. That would be our mafic. We can have an intermediate we call milk, in this case, milk chocolate. And then our felsic rocks in this case would be white chocolate. So in this case, we've got two rocks. They are both felsic, but the upper left rock is phaneritic, and the lower left rock is aphanitic. So they're both felsic, but the phaneritic one we're going to call granite, and the aphanitic one we're going to call rhyolite. Same minerals in both of them. If you squint, you can kind of see it. They're about the same color, same tonal value. Mafic rocks, again, rich in iron and magnesium and calcium, low in silica. They got a silica content of about 50% compared to 70% of the felsic. So if it's fine grain, we're going to call it basalt. That makes up the oceanic crust. If it's coarse grain, we're going to call it gabbro. So here's basalt, very fine grain. Here's gabbro. So the darker minerals in there are going to be maybe a little bit of olivine, some pyroxenes, maybe some amphiboles. The lighter colored minerals in this case are probably calcium plagioclase. And then here is a dark colored vesicular rock, and we call it scoria. Okay, so this is a felsic rock at Acadia National Park. This is a granite, 420 million years old. And we've got this dark mafic dike cutting it. A dike is simply a vertical igneous intrusion, tabular igneous intrusion. And then again, we can have an intermediate composition, what we call andesitic or intermediate, and we can have ultramafic, which is even richer in iron and magnesium or calcium. So this is a couple of different types of ultramafic. This is peridotite, made almost entirely of olivine, with maybe the darker ones probably being some pyroxene in there. And this is anorthosite, being primarily made of calcium plagioclase. This blue-gray color minerals are calcium plagioclase, primarily labradorite. And then here's a handy dandy chart we can put together that shows composition across the top. So let's stick with the felsic, intermediate, and mafic, and then texture along the y-axis here. Let's stick with phaneritic, aphanitic, porphyritic, and glassy. And then glassy, we can break down to frothy and vesicular. And so again, if it's phaneritic and felsic, we're going to call it granite. If it's If it is aphanitic and mafic, we're going to call it basalt. And different types of igneous rocks. We got large igneous bodies deep underground. We call them batholiths or plutons. We can have tabular igneous bodies underground. If they're vertical, we call them dikes. If they're horizontal, we call them sills. And then lava can flow out on the land surface and form what we call lava beds. Or sometimes if the lava is blown up into the atmosphere in tiny dust-like particles and lands down, we call those ash beds. Bowen's reaction series, just like water freezes at 32 degrees Fahrenheit or 0 degrees Celsius, these minerals have a solidification point, a temperature at which they solidify out of the magma. And when I talk about olivine and pyroxene, these aren't really individual minerals. These are families of minerals, okay? So olivine is a whole group of minerals. And so it starts cooling, it starts solidifying, crystallizing at about 1200 degrees Celsius, which is much, much, much hotter than your oven at home gets. And then after that is pyroxene, and then amphiboles, and then biotite. And then down here we got potassium feldspar, muscovite, and quartz. This is called the discontinuous series. The right side of the chart is called the continuous series because this is all the mineral group that we call plagioclase feldspar, okay? And it starts out calcium rich, okay? Feldspar would prefer to use calcium in its crystal structure. But if it runs out of calcium, it will substitute sodium for it. So it starts out at the higher temperatures using calcium, and as it starts cooling down, it starts running out of calcium and substitutes sodium for it. And so that's why we call it a continuous series. So this top layer up here is our ultramafic rocks. They're going to be made out of olivine, maybe a little bit of pyroxene or calcium-rich plagioclase. And then we got our mafic rocks, which may have a little bit of olivine, and then pyroxene and amphiboles, and again, calcium plagioclase are intermediate. And then down here are felsic, which are going to contain maybe a little bit of amphiboles and biotite, but mostly they're going to have potassium feldspar, maybe a little bit of sodium plagioclase, muscovite, and quartz. So again, probably not going to see quartz outside of felsic rocks, and we're not going to see olivine outside of ultramafic or mafic rocks. Magmas over time, as they cool and they use up various elements, the composition of the magma will change, and as a result of that, the rock type will change. So as the magma starts to cool, maybe it's starting to form olivine, these little green tabular crystals here. It's starting to form olivine, which needs a lot of iron. But over time, it uses up so much iron forming olivine that now it doesn't have enough iron to make olivine anymore. And so it starts making pyroxene instead. And so over time, you might see differences in the ratios of the different minerals in there. And so the final magma that results might have kind of layers in it where you've got like an olivine rich layer at the bottom, and maybe at the top you've got more of a amphibole rich layer. So that is crystal settling, and that's magmatic differentiation. So imagine you're making cookies, and you may start out making chocolate chip cookies, and you got a whole batch of chocolate chip cookies, but then you run out of chocolate chips, but you've still got sugar and flour and butter, so you switch, and maybe you make oatmeal raisin cookies or sugar cookies or something like that afterward. And that's similar to magmatic differentiation. And here's a jar of honey with crystals at the bottom and then clear honey at the top, and and I think you even got some little air bubbles in there, so that would be our vesicular texture. And so just an example of crystal settling. We think of ice floating on the top, but water ice is kind of unique. Most liquids, when they form crystals and solids, they tend to be denser than the liquid, and so they tend to sink down and settle at the bottom. Okay, so now getting to the national parks themselves. Yosemite National Park is located in California. It's in the mountain range we call the Sierra Nevada Mountains, which go a little bit into Nevada as well. They're a continuous mountain range that kind of go up and down the spine of California from the north all the way down to the south, and it's an old batholith. So here it is. This is a Google Earth image. And so these are the Sierra Nevada mountains, and this green boundary shows you Yosemite National Park. And the lighter colored areas on this are the exposed batholith, which is primarily made of granites and what we call granodiorites, kind of an intermediate rock. Here's Mono Lake over here, which is a very famous lake, by the way. And the darker colored areas are going to be forests. So again, Yosemite, the primary rocks at Yosemite National Park are what we call batholiths, or sometimes called plutons. They're not quite interchangeable, but they're similar. And this would have started out 210 to 95 million years ago as big blobs of magma underneath what is now California. And slowly over time, these magmas cooled and formed the rocks that we see at Yosemite today. And then later in the Cenozoic, this whole region was uplifted. These magmas formed deep underground, maybe in several miles underground. And the state of California was uplifted, and those overlying rocks were eroded, and these batholiths, these ancient batholiths and plutons, were exposed. And as a result of that, they fractured because as that overlying pressure was removed, the rocks expanded. But because these granites and granodiorites are not very flexible or elastic, they fractured. And so what we see here is this is a geologic map of Yosemite National Park. And basically the different colors represent different types of igneous rocks, whether we've got granites or granodiorites. And this is primarily a result of magmatic differentiation and crystal settling. And here's a view. I think this is taken from Glacier Point in Yosemite. It's been a long time since I've been to Yosemite. And so again, the area has been uplifted, the overlying rocks were removed, exposing these granites and granodiorites that we see here in Yosemite Valley today. And now they've got these very aesthetically pleasing waterfalls. And so this is the process of what we call unloading, where a rock forms deep underground under pressure. And you've got the pressure is from the weight of the overlying rocks pushing down on top of it. But as those overlying rocks are removed, as this pluton is uplifted, it's going to expand. But again, it's not very flexible. It's not very elastic. So as it expands, it's going to fracture. And these fractures are what we call joints. So here we can see lots of joints in these granodiorites at Yosemite. And this provides a couple of things. It provides zones of weakness that can later be eroded by rivers and ice. It also provides moisture in these fractures, some of the only moisture. And so those tend to be places where trees and shrubs grow. So this is actually nearby Sequoia National Park. Same rock types basically here. So we see these granites and granodiorites, and you see these giant slabs on here because you get kind of a layering appearance to this. This is called exfoliation. And so as the rock expands, it tends to expand. You get vertical joints or fractures, but you also get horizontal ones that parallel land surface, and it gives this kind of onion skin appearance to it. And this is from the book that the class is supposed to be using. And you can see the topography, and here's Yosemite Valley here. And this is another Google Earth image. So again, the lighter color areas are exposed granites and granodiorites. You can see these straight dark lines. These are going to be our joints that I'm talking about. And you can see how they appear like almost 90-degree angles to each other in a lot of cases. And the dark coloration, again, is because a lot of trees and stuff will grow in these joints because water will congregate in the joints, and it allows the trees to grow. Plus, it allows fractures for the roots to get down, whereas the solid granite and granodiorite is going to be too resistant for roots to get into it. John Muir, that we talked about in Module 1, he was the geologist, naturalist, who came to Yosemite in the 1800s. And he basically is the first person who said glaciers are what carved Yosemite Valley. The other geologists at the time kind of dismissed his ideas, didn't believe him. But now that's an accepted theory for how Yosemite Valley was carved. And this is what's called a benchmark. So you'll see these on a lot of mountaintops. These basically tell you the elevation. In this case, the elevation at this point where I took this picture was 7,214 feet above sea level. This kind of yellowish, here's the granodiorite that I'm talking about. Again, the dark minerals probably being biotite or hornblende. the pinkish minerals being potassium feldspar, lighter colored minerals being plagioclase. And this yellow is what we call lichen. Okay, it is a symbiotic relationship between an algae and a fungus. And it's one of the first pioneer organisms that grow on bare rock, and start to weather it and start to turn it into sediment and soils. And here's Bridal Veil Falls, one of the more spectacular waterfalls at Yosemite, with the moon rising or setting over it. Me there with like 1,500 of my closest friends. And Vernal Falls, this is a wonderful hike. If you go, you hike up this trail and you see Vernal Falls. And if you keep going, there's 2 or 3 other waterfalls along the hike. Outside of Yosemite National Park, just north of there, there's another national park called Lassen Peak, which is a volcano which last erupted in 1914. And these are ash layers, ash bed that formed from eruptions of what is now Lassen Peak. And the park has an abundance of wildlife. We get squirrels and deer. We get these type of just gorgeous birds called stellar jays. They're actually pretty common out in the western United States. This is an ancient type of plant called equisetum or horsetails. They evolved before the dinosaurs. They've been around for hundreds of millions of years, 300 million years. And Yosemite, as well as nearby Sequoia National Park, are famous for these giant sequoia trees. These can live to be 2,000, 3,000 years old and just get enormous, just gorgeous trees. Now we're going to switch to the East Coast. This is Acadia National Park, which is also predominantly a granite. So we can see here in this image, we can actually see some of the joints in this map. These vertical layers and some of the little coves here line up with these joints. So Acadia National Park was established in 1916 as a national monument and then upgraded to a national park in 1919. It is the first national park east of the Mississippi River. And again, we've got a granite, in this case, the Cadillac Mountain granite, which is 420 million years old. I honestly don't know a lot about the Cadillac Mountain granite, but we can see this shiny crystal here looks like muscovite, the darker ones again being hornblende, maybe some biotite in there. And again, the pinkish ones being potassium feldspar. And just showing you a little coast. So if you go up to Acadia National Park and the whole Maine coast, it's a rocky coast. There's not a lot of beaches there. Some of the beaches that they do have are gravel beaches as opposed to sand beaches. There are a few sand beaches, but it's a much more rocky coast, much different coast than we have down here in Florida. And this is near the top of Cadillac Mountain, which is the high point at the national park. And we can see some joints, again, similar to what we see in Yosemite National Park. And we can see, again, these blocks of granite sitting on other granite. So, almost a kind of exfoliation. And here's that same picture I showed previously with the Cadillac Mountain granite on either side being intruded by this mafic dike. And our principle of cross-cutting relationships tells us that features that cut across other features, the features doing the cutting must be younger than the other features. So the dike must be younger than the Cadillac Mountain granite. And now we're going to go back to California to Joshua Tree. So I took a group of students there in spring of 2019, I believe. Unfortunately, we stopped at the town sign and not the national park sign. So Joshua Tree is kind of at the southern end, near the southern end of Sierra Nevada, but closer to Los Angeles, maybe a couple hour drive from Los Angeles. And again, so the green line here is the boundary of Joshua Tree. And if you look closely here at the western boundary, we can see exposed rock, and we can again see these joints that have cut up the rock. And if we get a closer look, these particular types of rocks are called Monzo granites. And if I recall from my For my undergraduate, Monzo granites are a little bit depleted in silica compared to a normal granite, and so they tend to be richer in sodium. So you get a lot of sodium, some sodium plagioclase as well as potassium feldspars in there, not as much quartz. And so again, we see lots and lots of fracturing, lots of joints come from unloading and uplifting of these rocks. And as a result of that, you get this very, very blocky appearance to it. There was a country rock star back in the 60s and 70s named Graham Parsons, who was from Winter Haven, Florida, and he really loved Joshua Tree. So I'm a fan, so I'm throwing that in there. So the way, unlike Yosemite, you don't have towering elevations and big cliffs and stuff like you do at Yosemite. What you do have is you have lots of basically isolated little mounds of igneous rocks separated by flat valleys. And so as these igneous rocks were uplifted, some of them were eroded deeply, weathered deeply, others were uplifted and then fractured. And as the overlying soil and sediment were eroded away, you're left with these blocks of igneous rocks kind of stacked on each other. Great for bouldering if you do that. And here's another image, a Google Earth image. And so we can see this large patch of exposed Monzo granites here with all the fracturing, jointing going on here. So again, something at close to 90 degrees, not quite 90 degrees. We see that a lot in joints from crystals in there. But then you see some more isolated patches of igneous rocks exposed. These are called Inselbergs. And Joshua tree is named for these trees here. These are Joshua trees. They are a type of, similar to yucca tree, a type of, what are they? Type of agave, sorry. These can live for hundreds of years. They do not get to the huge size because of their desert conditions. They stay fairly small. They'll get to be 20 feet tall, 30 feet tall, or something like that. But nothing like on the order of the giant sequoias. But they can live, I believe, 500 years or something like that. Unfortunately, they live in very isolated areas, such as Joshua Tree. They have to have very, very specific temperatures and precipitation. It is believed that their seeds and fruits were eaten by giant ground sloths, which are not now extinct. And because of climate change, Joshua trees are starting to die out. In 2018, there was a government shutdown, and the National Park Service had to close because of lack of funding because of the shutdown. The shutdown had to do with federal budgets. And so the National Park Service had to close. Unfortunately, then President Trump ordered that the gates of the parks remain open so that people could access them. But that only led to vandals going into many of the parks and leaving trash, and in this case, destroying many of the Joshua trees. And it's a close-up. Very spiky trees. They got some beautiful blooms on them in the springtime, though. And now we're going to go to Hawaii Volcanoes National Park. It'll be the last one. And Hawaii, obviously, is a series of islands out in the Pacific Ocean, our 50th state. And there are 4 active volcanoes on Hawaii. There's Mauna Kea, that is the tallest peak. Mauna Loa, these are both basically kind of dormant right now. So Mauna Loa last erupted in the 1980s. There's another one up here. I don't remember the name. And then there's Kilauea, and that one currently is active. In fact, just as I record this on September 13th, 2023, there was an eruption earlier this week. I'm not sure if it's still going on this morning. So you can see these different kind of depressions here. These are craters, and you can see in this case in Kilauea, there's a whole line of craters which go along this ridge here. And these are the places that are the sources of actual eruption where the lava flows out onto the ground. So this is the big island of Hawaii, the largest island in the chain. And Kilauea is right here, and then Mauna Loa and Mauna Kea. So actually, go back up here just a second. Mauna Kea means white mountain. Mauna Loa means long mountain. And the Hawaiians believe that there are 2 sisters, goddesses, that live on here. I don't remember the name of the one at Mauna Kea, but she is the ice or snow goddess because actually Mauna Kea is at nearly 14,000 feet. So even though it's in the tropics, it will snow there. And Mauna Loa is a little bit lower, not quite the elevation. And because it has erupted more frequently, I guess, in the past, that goddess is called the fire goddess or lava goddess. So here's the crater, the main crater at Kilauea. So when I was there in 2014, I believe, it was not erupting. So there was a lava lake at the bottom of this crater. You couldn't get close to it. This picture I'm taking is as close as the visitor center would allow you to get. So I couldn't actually see the lava, except the glow at night. And here's a USGS image of the crater here and the lava lake below. And I believe that the eruption that was happening earlier this week was inside this crater, but it was happening with lava fountains that were tall enough you could see from the rim. This is Kilauea Iki, which I believe means son of Kilauea, and it's this flat valley floor because from 1959 to the mid 1970s, it was an area of continuous volcanic eruptions, and so you got layers and layers of lava pouring out and forming this flat valley floor. And now, nearly 50 years later, you can walk through there, and there are still fractures in the rock where hot steam and gases come up. But otherwise, it's safe to walk across there. Just bring plenty of water. It gets very hot, and there's no shade. And this is Mauna Kea, the view from our Airbnb at nearly 13,796 feet above sea level. It is actually the tallest mountain in the world. If you're going from its base, which is the sea floor, all the way up to its peak, it's actually like 3,000 feet taller than Everest. And this is the view of Mauna Loa from Mauna Kea. So that's Mauna Loa over there. And this is near the summit of Mauna Kea. You can drive up nearly to the summit of Mauna Kea. And at the summit of Mauna Kea, there are a whole bunch of astronomical observatories, telescopes, run by the United States, but some other countries as well. There is the Subaru telescope, which is owned and operated by the Japanese government. That's the only one that will give you a tour, or at least it did in 2014 when I was there. I highly recommend it if you're able to go. It's a great tour. It's a fascinating telescope to see. And then you can't quite drive to the summit, but you can hike to the summit from there. It's a short hike, but at nearly 14,000 feet, there's not a lot of air or oxygen. So so definitely pace yourself if you go, especially if you go directly from Florida. It is tall enough that it will get snow throughout the year. So, and at 14,000 feet, you're above a lot of clouds. So here's some radio telescopes. Stars emit all kinds of light, not just visible light, but they emit X-rays and gamma rays, but they also emit radio waves and microwaves. So astronomers use different telescopes to be able to monitor them. Now, Mauna Loa has a meteorological observatory, so they monitor weather and precipitation. And that is one of the places in the world where they monitor carbon dioxide in the atmosphere for climate change studies. So Hawaii formed as what we call a hotspot or a mantle plume. So supposedly, and again, not my real area of expertise, but there are these sources of magma that come from deep in the core mantle boundary and come up through the mantle and then burn through the crust and form volcanoes. There are, I think, something like 27 hotspots around the world. Other hotspots include Yellowstone, Iceland, the Galapagos. And so in this case, the mantle plume has been around for tens of millions of years, at least 65 million years, and it's stayed in the same spot, but the Pacific plate has moved over it. And in the process, it's basically burned through the Pacific plate and formed a chain of islands that we now call Hawaii. And if you go further away there, you got the Midway Islands. And then finally, waves have eroded them below sea level. So you got the Emperor Seamounts, which are underwater. Right now, the Big Island is centered over the mantle plume. There's actually a new volcanic island forming off the coast of the Big Island. Maui has a volcano which is still considered active, but I don't believe it's erupted since like the 1700s. And so the newest rocks are here at the Big Island, and then they're about a million years present up to about a million years old at Maui, about 1 to 1.5 million years old at Molokai, 2 to 3 million years old at Oahu. So the further away you get from the Big Island, the older the rocks and the older the islands are. So again, there's two main types of lava. These are again Hawaiian words. We got pahoehoe, which is ropey lava, and which is chunky lava. And again, the main difference is going to be the temperature, which is going to affect the viscosity. So the cooler the lava gets, as it's going to cool down, it's going to solidify and it's going to get thicker. And so when it's really hot, coming right out of the vent, right out of the crater, it's going to be fairly fluid. That's when you're going to get the ropey lava. As it flows away, it's going to cool down. It's going to get thicker. In other words, higher viscosity. That's when it's going to break up and form the chunky lava. So here's a benchmark near the Kilauea crater at 4,076 feet, I believe that says. And you can see the dark mafic rock around it. And this is some relatively recent lava flows, I think within the last decade. So you can see the really glassy nature as the surface of the lava cooled very fast, maybe within hours or something. And this kind of beautiful iridescent appearance that I was not expecting. And here's ropey lava. This is what we mean by pahoehoe or ropey lava. It looks like ropes. As the lava is very fluid, it gets kind of a crust on it, and that crust kind of rolls and bends, and that's how you get this ropey appearance. And here it was flowing around. I think this is like a little tree stump or something, so it flowed around a little tree stump. This kind of film on the lava. Obviously killed the tree in the process. And about a decade or two ago, it flowed across one of the roads in the national park. And so obviously the road is closed, and you can see the lava flowing across the road. And then this is an example of the chunky lava. So would not want to walk across that with bare feet. And then here we can see some chunky lava in the background. That's the darker stuff. And we can see some pahoehoe in the foreground. We get lots of these faults here as the weight of the lava piles up. The lava below gets compressed. And so that part of the island starts to sink and push down. And so you get some faults generating lots of small earthquakes, magnitudes 2s to 4s, I believe. Sometimes the lava will continue to flow underground, even though the surface hardens, and then it will pour out and empty. And so you get a cave that we call a lava tube. And a lot of these, some of these you can go into outside the national park. And inside the national park, they have one that you can go into. So this one was in, sorry, I can't remember the name of the town, on the west side of Hawaii, just on the side of the road. So my daughter and I hiked into that. And this is Thurston Lava Tube, which is inside the national park, and you can go into part of this. Mainly, they try to keep people out of the lava tubes because the lava tubes, they're the only native mammal on Hawaii is a bat. And so that's where the bat likes to go to roost and hibernate. And then also there's other, insects and life that live in the lava tubes. So again, you can see this kind of escarpment here, and you can see it here in this bottom picture in the bottom right. You can see these fractures here as the weight of the lava pushes down on the ocean crust, causes it to sink, and also compresses the rocks underneath. And rainbows are pretty common. You see they have a rainbow on their license plate because you just see rainbows everywhere. And you get as the lava is battered by waves, you get little erosional features, these sea cliffs and sea arches. It's very beautiful. There is this bird, a Hawaii goose, called a nene or nini. I'm not really quite sure how to pronounce it. And I guess the theory goes is that this is the descendants of a flock of Canada geese that got off course, maybe from a hurricane or something, as if you've seen the flamingos that were brought up to Florida and some other states as a result of Hurricane Adelia. a couple of months ago. And so maybe these Canada geese were blown off course. They landed in Hawaii, decided it was a good place to be and stayed, and evolved into what we now call Nene. There used to be thousands of these birds on the islands, all on all the islands, I guess. But between habitat loss and hunting, there's only a few hundred of them left. But if you go to the national park, you're almost guaranteed to see them. There are rainforests. These are koa trees, which are now a protected species. I was disappointed to see when you go to Hawaii that outside of the national park, you'll see very little native vegetation. People that have come in have basically all kind of replaced the native vegetation with exotic vegetation. But this is one place where you can see the native vegetation. So you've got rainforest because it gets a lot of rain on that part of the Hawaii. But it's easily fragmented and destroyed by lava flows. I'm not even going to try to pronounce this. I think it's, well, maybe I will. Lahua flower is called the flower, but the tree is called Ohia. Not sure I'm pronouncing that right. Okay. Okay, and this is a koa tree over here. Okay, and so again, the legend goes, I believe that it had to do with a prince and a princess that were in love, and I think Pele was jealous of the princess, so she turned her into the flower, and the prince was so upset that he begged Pele to turn him into the tree so that they could be together. I think that's a cute story. And these are called silver swords. As the rainforest, these are tree ferns here, which live in very few places, very, very ancient plants, but live in very few places around the world. And these are silver swords, which are native to the big island of Hawaii. But again, because of habitat loss, because of there are wild pigs on the island of Hawaii and some other wild animals, that many of these have been destroyed. So they only occur in a few places. And that concludes our presentation. So thank you very much. I hope you enjoyed it.